There is no place from which the Milky Way can be seen by human eyes in its entirety. We live inside it, buried among its stars, moving through one of its lesser spiral structures while dust conceals much of the greater design. Every image showing the galaxy from above is a reconstruction, assembled from measurements, comparisons, and the patient tracking of distant light. The familiar silver spiral exists beyond every possible human viewpoint. To see it whole, a traveler would first have to escape a system so vast that the escape itself could consume ages. The luminous disk spans roughly 100,000 light-years. Light entering one edge would need around 100,000 years to emerge from the other, despite moving almost 300,000 kilometers during every second of the journey. At the velocity of Voyager 1, a machine launched during the lifetime of people still alive today, the crossing would require well over 1 billion years. Continents would rearrange, species would vanish, new mountains would rise, and the sun would pass through several stages of its life while the craft continued through the galactic dark. A crossing of the Milky Way therefore becomes a journey through time as much as space. The ship cannot merely survive distance, it must survive the changing galaxy, the death of its builders, the evolution of its passengers, and the possibility that its destination will no longer resemble the place observed at departure. Every improvement in speed reduces the duration, though even the boldest imaginable propulsion leaves a traveler facing centuries, millennia, or longer. The galaxy is crossed only when a civilization learns how to carry its future farther than any memory can naturally reach. The number 100,000 light-years sounds precise because human language gives it a clean boundary. The Milky Way possesses no solid outer wall. Its stars thin gradually into darkness while streams, clusters, gas, dust, and a vast halo of dark matter extend far beyond the bright spiral disk. A traveler must first decide what crossing means. The conventional journey begins near one edge of the main stellar disk and ends near the opposite edge, following a path of roughly 100,000 light-years. A route through the wider halo could be considerably longer. Earth also occupies no convenient starting point. The solar system lies about 26,000 light-years from the galactic center and roughly halfway between that center and the visible outskirts. Traveling inward from the sun toward the central region would require around 26,000 years at light speed. Continuing through the center toward the far edge could bring the complete route from our position to approximately 75,000 light-years, depending on the chosen direction and the uncertain boundary of the disk. Crossing the entire diameter would require first reaching one edge or imagining a departure from a point humanity has never approached. A light-year measures distance through duration. It is the span crossed by light in 1 year, amounting to nearly 10 trillion kilometers. Multiplying that distance by 100,000 produces a number that resists ordinary comprehension. Kilometers become almost useless. The journey would cover close to a quintillion kilometers, a one followed by 18 zeros. Even errors of millions of kilometers would become invisible within the total. The scale also changes along the path. The galaxy contains crowded stellar regions, broad spaces between spiral arms, dense clouds, ancient clusters, remnants of dead stars, and enormous stretches where almost nothing interrupts the view. A straight line drawn across a map suggests one continuous road. The traveler would encounter a succession of environments formed across billions of years. Crossing the Milky Way would involve passing through its history, structure, and hidden dangers rather than simply covering a measured distance. The first useful comparison comes from the fastest machines humanity has already built. Voyager 1 moves away from the Sun at roughly 17 kilometers per second. During 1 hour, it covers more than 60,000 kilometers. During 1 year, it travels hundreds of millions of kilometers. That performance has carried it beyond the heliosphere, into the interstellar environment surrounding the solar system, farther from Earth than any other functioning human creation. Against the Milky Way, Voyager's achievement becomes almost motionless. At a constant speed near 17 kilometers per second, covering 1 light-year would require about 17,500 years. The nearest star system would remain more than 70,000 years away. A full crossing of the galactic disk would require roughly 1.7 billion years. Voyager would spend longer in flight than complex animals have existed on Earth. No spacecraft could realistically operate unchanged for that duration. Radioactive power sources decay, circuits degrade, surfaces erode, and microscopic damage accumulates. Voyager was constructed for a mission measured in years and has survived for decades through exceptional engineering and careful management. Extending the same principle across a billion years would require materials and repair systems beyond any present experience. A single component with a tiny annual chance of failure would become almost certain to fail across such an interval. The galaxy would also evolve during the passage. Stars now visible along the route would move far from their present positions. Many would die. Others would form from collapsing clouds. Spiral patterns would shift. The solar system would complete several orbits around the galactic center. Andromeda would approach and merge with the Milky Way long before the hypothetical Voyager completed its crossing. The destination chosen at launch would belong to an ancient map. This calculation reveals the central problem. Current spacecraft speed belongs to the scale of planets and the outer solar system. Galactic distance belongs to another order of reality. Refining the same engines would produce limited gains. A journey across the Milky Way requires a form of propulsion, endurance, and civilization, unlike anything that currently exists. Parker's solar probe has traveled faster than any human-made object, reaching approximately 700,000 kilometers per hour during close passes around the Sun. Its speed comes largely from falling deep into the Sun's gravity and following an orbit designed through repeated encounters with Venus. At its fastest, it moves close to 200 kilometers per second, more than 10 times the outward velocity of Voyager 1. If that peak speed could somehow be maintained in a straight line across the Milky Way, the conventional 100,000 light-year journey would still require around 156 million years. The first mammals lived during a world closer to that distant departure than modern humans would be to the arrival. Entire branches of life could emerge and disappear while the probe moved through only part of the disk. Parker's record also carries an important limitation. The spacecraft reaches its greatest velocity while passing extremely close to the Sun. It cannot simply redirect that motion toward another star and preserve every advantage of the orbit. A vehicle intended for galactic travel needs a propulsion system capable of generating and maintaining its own trajectory. The fastest measured speed does not automatically become an available cruising speed. Suppose engineering advanced enough to increase Parker's performance by another factor of 100. The resulting vehicle would move at nearly 20,000 kilometers per second, around 7% of light speed. Crossing the Milky Way would still take roughly 1.5 million years from an external perspective. The leap from modern machinery to such a craft would be immense. The journey would remain longer than the history of our species. Speed improves travel time linearly at low relativistic velocities. Doubling speed halves the duration. Crossing distances of 100,000 light-years requires improvements measured through extraordinary factors. 10 times faster remains slow. 1,000 times faster remains slow. The galaxy forces technology to compete against a distance chosen by billions of years of cosmic formation. Chemical rockets cannot provide the necessary transformation. They accelerate by expelling reaction mass, drawing energy from chemical bonds whose available energy per kilogram remains limited. Chemical propulsion works extremely well for escaping planets, adjusting orbits, and beginning journeys through the solar system. The exhaust velocity constrains the final speed, and carrying more propellant increases the mass that must itself be accelerated. The rocket equation creates a severe penalty. Achieving a large change in velocity requires an exponential increase in the ratio between initial mass and final mass. Tanks grow to hold fuel that accelerates fuel needed for later acceleration. Stages can be discarded, gravity assists can borrow momentum from planets, and trajectories can exploit natural forces. These methods provide remarkable results within a planetary system. They cannot bring a crewed vessel to a meaningful fraction of light speed. Nuclear propulsion offers greater energy density. Fission reactors could heat propellant or generate electricity for high-efficiency engines. Fusion concepts could use reactions similar to those powering stars, converting small amounts of mass into substantial energy. A successful fusion drive might reach speeds far beyond current probes, perhaps allowing voyages to nearby stars over decades or centuries under optimistic assumptions. A galactic crossing would remain vast. At 1% of light speed, the journey across 100,000 light-years requires about 10 million years, excluding acceleration, deceleration, navigation, and detours. At 10%, it requires 1 million years. At 20%, roughly 500,000 years. A vessel moving at half the speed of light still spends about 200,000 years crossing the disk, according to observers at rest with the galaxy. These durations exceed the stable lifespan of known political systems, languages, religions, technologies, and civilizations. Building a fast engine solves one layer of the problem. The travelers also need a society capable of continuing through periods longer than recorded human history. Every assumption about command, maintenance, education, purpose, and identity must survive more change than any institution has yet endured. Antimatter offers one of the highest known energy densities permitted by established physics. When matter meets antimatter, their mass can be converted into other particles and radiation. In principle, this process could provide far more energy per kilogram than chemical or nuclear reactions. Antimatter propulsion appears frequently in proposals for relativistic spacecraft because it could reduce the enormous quantity of fuel required. Producing antimatter is currently inefficient and extraordinarily expensive. Humanity creates tiny amounts in particle accelerators, far below the quantities needed for propulsion. Storing it introduces another difficulty. Antimatter cannot touch ordinary matter without annihilating. It must be suspended through electromagnetic fields, contained reliably through acceleration, vibration, radiation exposure, and decades or centuries of operation. A failure involving even a modest fuel reserve could destroy the spacecraft. Heat from propulsion must also be managed. Space provides no surrounding air or water to carry waste heat away. The ship must radiate energy through large surfaces, and those radiators become vulnerable structures. A powerful engine can produce enough thrust to accelerate the vessel while simultaneously creating a thermal problem capable of ending the mission. Even a successful antimatter vessel would remain beneath light speed. Suppose it reached 90% of that limit. From the perspective of the galaxy, 100,000 light-year crossing would require a little over 111,000 years before accounting for acceleration and slowing. Relativistic time dilation would reduce the duration experienced aboard, though the external galaxy would continue aging throughout the passage. At higher speeds, the experience time can shrink dramatically. The energy requirement rises just as dramatically. Every additional fraction near the limit costs more than intuition expects. 99% of light speed offers a different journey from 90%. 99.9% changes it again. The ship approaches a boundary that can never be reached by an object with mass. Antimatter could transform interstellar travel if a civilization learned to manufacture and control it safely. Crossing the Milky Way within an ordinary human lifetime would demand velocities so close to light speed that energy, shielding, navigation, and causality become the defining challenges. The fuel alone cannot solve the voyage. Relativity changes the answer according to the observer asking the question. An astronomer remaining near Earth measures the distance across the galaxy and watches the ship travel beneath the speed of light. From this external frame, no crossing of 100,000 light-years can take less than about 100,000 years. Acceleration and deceleration make the duration longer. The passengers may experience much less time. As a spacecraft approaches light speed, time aboard passes more slowly relative to clocks left behind. Length contraction also reduces the distance measured in the ship's frame along the direction of motion. These effects belong to the same geometry of spacetime. They allow travelers to cross a distance that appears enormous from Earth while aging through a smaller interval. At 90% of light speed, the time experienced aboard during the cruising portion would remain tens of thousands of years. At 99%, it would fall to around 14,000 years for a 100,000 light-year route. At 99.9%, the experienced crossing could shrink to several thousand years. Pushing still closer to the limit could eventually bring the subjective journey within centuries or decades. The energy grows without bound as the velocity approaches light speed. A ship large enough to support human life would carry enormous relativistic kinetic energy. Any collision would become catastrophic. Turning the vessel would demand forces applied across vast distances. Slowing at the far edge would require removing the energy invested at departure. The external universe would age by at least 100,000 years. The travelers could arrive having experienced decades while every society they knew passed into ancient history. A return voyage would deepen the separation. They might leave a young civilization and come back after 250,000 years, carrying memories from an era preserved only in archives. Relativity therefore allows a form of rapid personal travel while preserving the vast duration of the galactic crossing. The galaxy can become smaller for the travelers, though the journey still carries them irreversibly into the future of everyone else. Acceleration determines whether a relativistic voyage could be endured by humans. A ship could theoretically accelerate at a rate similar to Earth's gravity, allowing passengers to experience a continuous force beneath their feet. The interior would gain an apparent downward direction. After months and years of acceleration, the vessel would approach light speed while relativistic effects became increasingly important. In an ideal calculation, continuous acceleration at 1 Earth gravity produces extraordinary results. The crew could reach the center of the Milky Way within a few decades of subjective time, turn the ship, and decelerate during the second half. A full crossing could fit within a human lifespan aboard. Tens of thousands of years would pass in the galaxy outside. This elegant scenario hides immense engineering demands. Maintaining 1 gravity of acceleration for years requires continuous power on a scale far beyond current civilization. The engine must propel the ship, its fuel, shielding, radiators, habitats, spare parts, food systems, and every passenger. As velocity increases, the energy required to sustain further acceleration rises according to relativistic physics. The ship must also reverse orientation at the midpoint. Acceleration changes direction so that the vessel can slow before reaching the destination. Any failure late in the journey could send it racing beyond the galactic edge with no practical method of rescue. The target itself moves while the ship travels. Navigation must predict the future position of a region tens of thousands of years ahead in the galactic frame. A continuous 1-gravity journey remains useful because it reveals that human aging is not the absolute barrier. Physics permits travelers to experience a much shorter interval than distant observers. The required technology approaches the edge of imagination while staying within relativity. The passengers could cross the Milky Way and survive biologically. Their civilization of origin would be separated from them by an age longer than the whole span of written history many times over. At relativistic speed, empty space becomes dangerous. The space between stars contains atoms, ions, dust grains, radiation, and larger objects. Its density is extremely low by terrestrial standards. A spacecraft crossing 100,000 light-years encounters an immense column of material simply because the path is so long. A grain of dust weighing a fraction of a gram can release devastating energy when struck near light speed. Individual hydrogen atoms enter the ship's frame as high-energy particles, producing radiation and secondary cascades when they collide with shielding. The front surface of the vessel becomes exposed to a continuous beam generated by its own motion through the interstellar medium. Shielding with ordinary material adds mass, demanding more propulsion energy. A thick sacrificial barrier could gradually erode. Magnetic or electric fields might redirect charged particles, though neutral dust remains difficult. The spacecraft could project material ahead of itself, use lasers to break apart approaching grains, or travel behind a cloud of protective particles. Each solution introduces new systems that must function over the entire crossing. Detection is another challenge. At near light speed, the time between seeing an obstacle and striking it becomes extremely short. Light from the obstacle reaches the ship only slightly before the ship itself arrives. A sensor cannot provide unlimited warning because information also travels at light speed. Navigation would depend upon mapping the route in advance and clearing hazards far ahead. The galaxy contains regions where gas and dust are denser, especially within molecular clouds and star-forming areas. A direct path through such a region could be impossible at extreme velocity. The vessel might choose a route above or below the thin stellar disk, traveling through the galactic halo where matter is sparse, then descend near the destination. This detour could increase distance while improving survival. The fastest route in a geometric sense may become the worst route in physical terms. A successful crossing would follow a carefully chosen corridor through a moving galaxy, balancing distance, matter density, radiation, available stars, and possible repair sites. Traveling through the galactic plane would bring the ship past an extraordinary variety of systems. The average distance between stars near the Sun is several light-years, though stellar density changes across the galaxy. Toward the central regions, stars become far more crowded. In the outer disk and halo, the spaces grow wider. A ship moving slowly enough to stop regularly could use stars as islands. Each system might provide energy, raw materials, and opportunities for repair. The journey would become a chain of interstellar passages rather than one uninterrupted crossing. Settlements could be founded along the route, creating a gradual expansion through the galaxy. This strategy abandons speed in favor of continuity. A civilization might send missions to nearby stars, wait for colonies to mature, and let each colony launch new missions. Even vessels traveling at a small fraction of light speed could spread life across the Milky Way within millions or tens of millions of years. The original travelers would never reach the far edge. Their descendants, cultures, machines, or biological creations would complete the crossing. The route would resemble the movement of a living frontier. Some branches would fail. Others would remain around their stars and stop expanding. A few would continue outward. After enough time, independent waves of settlement could meet after evolving separately for thousands of generations. The question, how long would it take us to cross the Milky Way, then acquires several meanings. One crew might cross, one lineage might cross through successive generations. A network of colonies might spread from one edge to the other. Machines could carry human knowledge farther than biological people. Each interpretation produces a different timescale and a different definition of arrival. A civilization has already crossed a territory when its influence reaches the far side, even though no individual has traveled the full distance. Human history on Earth followed this pattern. Languages, technologies, crops, and populations spread through chains of shorter journeys. The galaxy could be crossed through the same principle on a scale measured in light years. A direct generation ship would require an inhabited world enclosed within machinery. At 10% of light speed, a full crossing lasts around 1 million years in the galactic frame, with only a modest relativistic reduction aboard. Assuming an average human generation of 25 to 30 years, tens of thousands of generations would be born and die before arrival. The original mission would become older than the species that launched it. Every language spoken at departure would evolve beyond recognition unless deliberately preserved. Religions, laws, family structures, and ideas of personal identity would change. The vessel would experience conflicts, reforms, discoveries, and periods of decline. Its history would become longer than the remembered history of Earth. Maintaining a purpose across that duration may prove harder than maintaining an engine. The first crew would understand the reason for departure. Their distant descendants might regard the destination as an inherited demand imposed by people who vanished a million years earlier. They could choose to stop around another star, alter the route, divide the vessel, or abandon the crossing entirely. Biological evolution would continue. Natural selection within the ship, genetic drift, medical intervention, and deliberate modification could produce descendants physically different from the founders. They might become adapted to artificial gravity, controlled climates, limited ecosystems, or entirely digital existence. The beings reaching the far side could have only a distant ancestral relationship with present humanity. The ship must preserve genetic diversity and ecological stability through more generations than any closed human environment has supported. Microorganisms would evolve quickly. Crops and human pathogens would change. Small imbalances in nutrients or atmospheric chemistry could accumulate. A system designed at departure might undergo millions of repairs and redesigns. Calling such a vessel a ship becomes increasingly inadequate. It would be a moving civilization, a biosphere, a historical world, and perhaps a branching collection of societies. The Milky Way would be crossed by something that began as a spacecraft and arrived as a new form of life. Suspended animation could reduce the social burden by allowing passengers to sleep through most of the voyage. Human hibernation remains beyond current medical ability, especially for centuries or millennia. Lowering metabolism introduces risks involving tissue damage, infection, circulation, bones, muscles, brain function, and the long-term stability of every cell. A million-year suspension would demand an almost perfect preservation process. Radiation damages DNA and molecular structures even when metabolism is slowed. Cooling cannot stop every form of decay. The chamber, computers, power systems, and repair machines must continue operating while the passengers remain unable to intervene. Embryos, reproductive cells, and genetic archives may be easier to preserve than living adults. An automated vessel could carry frozen material, artificial wombs, educational systems, and machines capable of raising the first generation near the destination. The crossing would occur without conscious human travelers. Humanity would be reconstructed at the far side from biological potential and cultural records. This approach creates difficult questions about parenthood and identity. Children born after a million-year voyage would never meet the people who designed their society. Machines would select when and how they entered life. Their knowledge of Earth would come from archives maintained through an interval longer than the existence of many species. Digital minds might survive more easily, provided information can be copied, corrected, and migrated between durable systems. A digital traveler could remain inactive for most of the flight and awaken during repairs or arrival. Data still requires physical storage. Radiation, impact, software corruption, and manufacturing errors threaten the underlying machines. No preservation method removes the need for maintenance. The journey lasts long enough for every passive object to degrade. Survival depends upon active systems capable of detecting faults, constructing replacements, updating knowledge, and adapting to conditions never predicted by the builders. Self-replicating spacecraft could cross the galaxy without requiring any machine to survive the complete distance. A probe reaches a star system, gathers local material, builds several copies, and sends them toward neighboring stars. Each generation travels only a few light years. The wave of replication advances through the disk. If the probes move at 10% of light speed and require centuries to establish factories at each destination, expansion could still spread across the Milky Way within a few million years. Faster replication and travel would reduce the duration. Slow or failed branches would be compensated by successful branches moving through other routes. The advantage comes from renewal. Every new probe begins with recently manufactured components. Damage accumulated during one passage does not have to be carried across the entire galaxy. The network uses stars and planets as sources of energy and matter, replacing the impossible demand for one immortal spacecraft with a sequence of temporary machines. The danger lies in control. Instructions copied millions of times can mutate through error, deliberate modification, or adaptation. A probe designed to explore may begin consuming resources in ways its creators never intended. Safeguards could degrade. Different branches might encounter one another after evolving incompatible goals. A self-replicating network could also carry life. It might transport microbes, seeds, embryos, digital minds, or manufacturing systems capable of building habitats. The crossing would become a process of propagation. By the time the wave reached the far edge, The solar system would receive reports millions of years old, assuming any connection remained. This may represent the most realistic method for a civilization to cross the Milky Way under known physics. The duration remains immense to an individual and relatively brief compared with the galaxy's age. The Milky Way has existed for billions of years. A replication wave lasting several million years would occupy only a small fraction of its history. The central region presents one of the most dramatic stages of the journey. From Earth, the galactic center lies around 26,000 light-years away, hidden at visible wavelengths behind dust. At its heart sits Sagittarius, a star, a supermassive black hole with a mass of several million suns. Stars orbit close to it at extraordinary speeds. A traveler crossing directly through the center would enter a dense and energetic environment. Stellar encounters become more frequent. Radiation from compact objects, hot gas, and violent events increases. Supernova remnants, neutron stars, black holes, and powerful magnetic structures contribute to a landscape far harsher than the solar neighborhood. The black hole itself occupies a tiny region compared with the galaxy. A ship could pass far from its event horizon while still traveling through the central bulge. Gravity would affect the route, and precise navigation could use the galactic potential rather than fighting it. The central region could serve as a gravitational turning point or a source of energy for an advanced civilization. Passing near the center may shorten a geometric route between opposite edges, though a path slightly above or below the plane could offer greater safety. The traveler must decide whether a direct crossing means following a diameter through the heart or choosing the fastest survivable trajectory through three-dimensional space. Civilizations could be more common near regions with many stars, offering opportunities for contact or danger. The high density also exposes planetary systems to gravitational disturbance and radiation. The actual distribution of life remains unknown. A route chosen for access to inhabited systems could differ completely from one designed for speed. From the center, the Milky Way would no longer resemble the soft band visible from Earth. Stars would fill the sky with extraordinary intensity. The distant spiral arms would curve around the traveler, though dust would still conceal much of the grand design. Even there, the galaxy could never be seen whole without climbing thousands of light-years above its disk. Leaving the plane of the Milky Way creates another possible crossing. The stellar disk is roughly 100,000 light-years wide and much thinner in its vertical dimension. Most ordinary stars occupy a layer only thousands of light-years thick, though the central bulge, thick disk, and halo extend farther above and below. A ship could first climb out of the crowded plane, travel across the galaxy through the sparse halo, then descend toward the far edge. This route resembles an aircraft rising above difficult terrain before crossing it. The total distance increases because the ship follows the sides of a broad triangle rather than a straight line along the disk. The halo contains old stars, globular clusters, streams left by absorbed dwarf galaxies, hot gas, and dark matter whose presence is inferred through gravity. Matter remains sparse over much of the route. A relativistic craft would benefit from lower collision risk, though finding fuel, repair material, or inhabited systems would become harder. Traveling 10,000 light-years above the plane would provide an extraordinary view. The spiral disk could finally appear as a vast, luminous structure beneath the ship, crossed by lanes of dust and surrounding a bright central bulge. The image would develop over thousands of years of external travel. At relativistic speed, the view would be distorted by aberration, Doppler shifting, and the concentration of incoming light toward the direction of motion. The Milky Way would also move during the crossing. Stars orbit the center at different rates, and spiral structure changes. A traveler outside the disk could observe patterns shifting across tens of thousands of years. The galaxy at arrival would present a different arrangement from the one seen at departure. The safer path may therefore produce a longer and more isolated mission. It trades encounters with matter for an immense passage through emptiness. The vessel would cross above a galaxy full of stars while remaining thousands of light-years from any possible refuge. Navigation across the Milky Way cannot rely upon a static map. The Sun orbits the galactic center at hundreds of kilometers per second and requires roughly 240 million years to complete one revolution. Other stars follow their own orbits. Molecular clouds disperse, clusters dissolve, and gravitational encounters alter trajectories. For a voyage lasting 1 million years, stellar motion becomes substantial. A star moving at 30 kilometers per second travels around 100 light-years during that interval. Faster stars cover greater distances. A destination chosen from an image seen at departure may move far from its recorded position before the spacecraft arrives. Astronomers would predict future locations through measurements of position, distance, velocity, and gravitational influence. Accuracy must remain high across enormous time. A tiny error in velocity grows into a major positional error after thousands of years. The target's unknown planets add another layer of motion. The spacecraft could update its route as new observations became available. Light from the target still arrives with delay. A star 10,000 light-years ahead is observed as it existed 10,000 years earlier. Its current position must be inferred. Near arrival, the delay shrinks and navigation becomes more precise. Autonomous systems would handle most decisions. Instructions from Earth could require thousands of years to arrive. By the time Mission Control responded to a new obstacle, the spacecraft would have crossed a vast region. The vessel must contain its own astronomers, engineers, maps, and decision-making authority. A galactic crossing would be planned as a prediction of moving objects through four-dimensional space-time. The destination is a future meeting point rather than a fixed place. Every successful arrival means that the ship and target have followed calculated paths through a changing gravitational system. Communication with the ship would fade into history. During the early phase, messages might take years or decades to travel between Earth and the travelers. The delay grows continuously. After the ship passes the galactic center, a single exchange could require more than 50,000 years. Earth would receive records describing events that occurred before entire civilizations rose and fell. A message announcing a birth aboard might arrive after thousands of generations had followed that child. Any reply would be addressed to descendants living in a future beyond prediction. The ship would receive an equally ancient Earth. News arriving from home would describe a planet tens of thousands of years behind its current condition. The travelers could preserve a sequence of delayed transmissions, watching the solar system's old history unfold while knowing that its present remained inaccessible. Communication beams also weaken across distance. A laser can remain narrow, though diffraction causes spreading. The transmitter must aim toward a moving target whose future position is uncertain. Receivers require large collecting areas and sensitive instruments. Dust, gas, gravitational lensing, and background radiation complicate detection. Relay stations could form a chain across the galaxy. Each station receives, amplifies, stores, and retransmits information. The network reduces signal loss and provides local communication between neighboring regions. It cannot remove the speed of light delay. A message still needs tens of thousands of years to cross the disk. The concept of mission control eventually disappears. Earth can preserve ceremonial authority, scientific interest, or historical connection. Practical decisions belong to the ship. Distance turns every expedition into an independent society long before it reaches the far edge. During a 100,000-year voyage near light speed, the galaxy changes in subtle and dramatic ways. Thousands of massive stars complete their lives. New stars form inside cold clouds. Planetary systems emerge. Supernova explosions enrich surrounding space with heavier elements. Compact remnants travel through the disk. The spiral arms are patterns of density and star formation rather than rigid structures rotating as one solid object. Stars move into and out of them. A route that begins along one arm may end after the local structure has shifted. Names given to the arms by distant astronomers carry less meaning when the traveler experiences their gradual transformation. Humanity's solar system also moves. If a ship crossed the galaxy and later attempted to return, the sun would no longer occupy its departure position. After 200,000 years, it would have traveled a noticeable distance along its galactic orbit. The route home would lead toward a moving star in a changed neighborhood. A million-year crossing at 10% of light speed allows larger transformations. Earth's climate and species could change. Human descendants might spread to other stars, alter themselves, or disappear. The travelers could reach the far side after the civilization that launched them had already crossed by another route. A journey lasting hundreds of millions of years would encounter a different galaxy. Stellar populations would age. Galactic mergers and interactions could reshape the Milky Way. The boundary between crossing a place and crossing its future would vanish. Every duration produces its own destination. A fast ship arrives at the far edge of the current Milky Way's near future. A slow ship arrives at a galaxy transformed by cosmic history. Travel time determines the world being reached as strongly as direction does. The collision between the Milky Way and Andromeda is expected to unfold over billions of years. The two galaxies approach under mutual gravity and will pass through one another, generating tidal structures and eventually forming a merged system. Individual stars are so widely separated that direct stellar collisions should remain rare, though their orbits will be rearranged. A Voyager speed crossing lasting roughly 1.7 billion years would occupy a substantial fraction of the interval before the major stages of this encounter. The craft could depart from the Milky Way and find the galactic environment changing as Andromeda grew larger in the sky. Its chosen destination might be displaced by gravitational disturbance before arrival. A slower hypothetical object could begin in one galaxy and end within a merged structure that no longer possessed the original boundary. Asking whether it had crossed the Milky Way would become historically complicated. The galaxy at departure would survive through stars and matter while losing its separate form. This comparison shows how extreme current spacecraft speeds appear on galactic scales. The universe does not wait for a slow traveler. Galaxies orbit, merge, and evolve. Stars age. A journey lasting billions of years competes with the lifetime of astronomical structures themselves. Relativistic travel avoids much of this transformation by reducing the external duration toward the light-crossing time of the disk. 100,000 years remains short compared with the Milky Way's age. The spiral structure would change, while the galaxy would remain recognizably the same large system. The meaningful threshold for crossing the Milky Way may therefore lie far above the speed needed merely to reach another star. A civilization capable of traveling at 10% of light speed can settle nearby systems. A civilization approaching light speed can contemplate the galaxy as a destination that remains physically coherent throughout the voyage. Wormholes offer a theoretical route around distance. A wormhole would connect two regions of space-time through a shorter internal path. Entering one mouth and leaving another could allow a traveler to cross the galaxy without moving locally faster than light. The true journey length would depend upon the geometry inside the connection. General relativity contains mathematical solutions resembling such passages. Keeping a traversable wormhole open may require exotic conditions, including negative energy arranged in quantities and forms beyond demonstrated technology. Stability, radiation, tidal forces, and quantum effects create additional obstacles. A wormhole also needs an exit. Creating a passage to the far side of the Milky Way may require first transporting one mouth there through ordinary space. The initial construction could take at least as long as a conventional voyage. Once established, later travelers might cross quickly. If naturally occurring wormholes exist, their locations and properties remain unknown. A network could transform galactic geography. Regions separated by 50,000 light-years in ordinary space might become neighbors through a stable connection. Political and cultural unity could then follow the topology of the network instead of the shape of the spiral disk. Causality creates serious concerns. Certain arrangements of moving wormhole mouths could allow paths into the past according to external observers. Quantum physics may prevent such configurations or make them unstable. A usable wormhole would involve more than a tunnel through space. It would alter the ordering of events. Without evidence that traversable wormholes exist, they remain possibilities within theoretical exploration. They illustrate the scale of the required breakthrough. Crossing the Milky Way rapidly would demand mastery over space-time itself beyond the development of a stronger engine. Warp drive geometries present another speculative approach. The idea places a spacecraft inside a region where space-time contracts ahead and expands behind. The vessel remains locally within its own small environment while the surrounding geometry carries it across a large distance. Early mathematical models required negative energy in extreme conditions. Later studies have explored variations, energy requirements, and relationships with known relativity. No experiment has produced a warp region capable of transport. No engineering path currently explains how to create, control, accelerate, or stop one safely. A warp bubble crossing the Milky Way could in principle reduce travel time for external observers if effective faster-than-light motion were possible. Communication with the front of the bubble, interactions with matter, horizon formation, and the release of accumulated radiation raise difficult problems. The ship may be unable to control the geometry from inside once it forms. Faster-than-light motion also threatens causality. In relativity, observers moving differently divide space and time differently. A method that allows signals to outrun light can often be arranged into a closed path returning information to an earlier event. The problem reaches into the consistency of cause and effect. Warp concepts remain valuable as tests of physical theory. They force researchers to examine which geometry's equations permit and which energy conditions nature allows. Their presence in mathematics provides no guarantee that a civilization can build them. A conventional galactic crossing remains bounded by 100,000 years in the galaxy's frame. Every proposal offering a shorter external time must confront the structure of relativity. The journey becomes an investigation into whether distance itself can be engineered. The safest way to cross the Milky Way may involve accepting a very long duration and building continuity across it. Instead of one ship, humanity could create a chain of habitats, stations, colonies, archives, and communication relays. Each generation extends the network by a few light years. The front might advance slowly while the territory behind becomes densely connected. Travelers near the edge encounter young settlements. Regions close to Earth accumulate thousands or millions of years of cultural history. There would be no single galactic civilization sharing one present. There would be a moving gradient of ages, languages, technologies, and identities. The first message announcing arrival at the opposite edge would require another 100,000 years to reach Earth. By the time it arrived, the successful colony would already possess an ancient history. Earth might have forgotten the original expansion project or transformed beyond recognition. A physical object could then be sent along the established route, stopping at settlements for repair and resupply. It might eventually cross the disk after millions of years, carrying a ceremonial record from the first world to the last. Most of its components would be replaced along the way. The object's identity would survive through continuity rather than unchanged material. Humanity itself could function in the same way. No original traveler reaches the far side. Genes, ideas, machines, and memories move through successive populations. Each settlement hands part of the inheritance onward. This method resembles the slow movement of life across Earth. No individual organism crossed every landscape involved in a species expansion. Populations moved, divided, adapted, and carried ancestry into new regions. A galactic crossing may occur through the migration of a lineage whose members each travel only a small fraction of the total distance. A civilization capable of such expansion must consider ethics across extraordinary intervals. The people who begin the project decide that distant descendants will continue it. Those descendants inherit risks, duties, and destinations chosen before their birth. The longer the crossing, the weaker the original consent becomes. A generation ship may require population control, compulsory maintenance, restricted access to resources, and education designed around mission continuity. These policies could preserve survival while limiting individual freedom. Future inhabitants might challenge the legitimacy of rules written thousands of years earlier. Stopping could be a reasonable choice. A ship reaching a stable star system may find planets, materials, and opportunities for settlement. Continuing toward an abstract far edge could appear wasteful. The mission's symbolic goal might conflict with the immediate welfare of living people. Machines face a related question. Self-replicating probes programmed to cross the galaxy may consume resources in systems containing life. Their objective could cause harm across millions of worlds. A civilization must design limits that remain meaningful after the creators lose every ability to supervise the network. Crossing the Milky Way becomes an ethical project because its duration transfers consequences into the hands of unknown beings. Engineering can calculate velocity and fuel. It cannot determine whether a promise should bind a population 100,000 years later. The most responsible plan may preserve choice. Each generation receives the knowledge and capability to continue while retaining the authority to alter the route. The galaxy would be crossed through repeated consent rather than obedience to a single ancient command. What would arrival mean at the opposite edge? The boundary contains no gate, line, or sudden change. Stars become gradually less common. The bright disk fades into the halo and intergalactic darkness. A traveler would choose a conventional point and declare the crossing complete. From that distant region, the Milky Way would extend behind the ship. To see the galaxy as a spiral, the travelers would need to climb far above or below its plane. From the edge, they would see a brilliant band broadening toward the center, filled with the combined light of stars crossed during the journey. Earth would be a faint point tens of thousands of light years away. Any image received from the solar system would show a remote past. If the crossing took place near light speed, Earth's current transmission at arrival would describe the era around departure. The travelers would have physically entered the future while continuing to see their origin through old light. They might send a message announcing success. The signal would begin another crossing without them. It would pass every system visited along the route, reaching each one at a different stage of its history. Earth would receive it after a duration comparable to the original voyage. The arrival ceremony could therefore have no immediate audience beyond the local passengers. Every observer elsewhere remains separated by delay. Completing the crossing is a local event whose meaning spreads slowly across the galaxy. The final border would feel quiet. No cosmic mechanism recognizes that a civilization has traversed the disk. The achievement exists through memory, records, and the decision to name the journey complete. The shortest physically established answer is around 100,000 years. That duration belongs to a beam of light moving across the main stellar disk from edge to edge. A massive ship must take longer in the Milky Way's frame. Starting from the solar system and traveling toward the far edge could reduce the distance to roughly 75,000 light-years along a suitable direction. At Voyager 1's speed, the full disk crossing approaches 1.7 billion years. At Parker Solar Probe's record velocity, sustained through impossible circumstances, the crossing would still require roughly 156 million years. At 1% of light speed, 10 million years pass. At 10%, 1 million. At half-light speed, around 200,000 years. At 90% of light speed, the external voyage lasts a little over 111,000 years. The passengers experience a shorter period through time dilation, though still far beyond ordinary lifetimes. At velocities extraordinarily close to light speed, a continuously accelerating crew could experience decades while the galaxy ages through more than 100,000 years. A wave of self-replicating probes or colonies might spread from one side to the other in several million years, depending on speed and time spent in each system. This approach crosses through propagation rather than one continuous flight. Wormholes or warp geometries could change the answer radically if nature permits their construction. Every number describes a different journey. The fastest external crossing is governed by light. The fastest subjective crossing is governed by relativity, energy, and survivable acceleration. The most plausible civilizational crossing may occur through many short voyages linked across generations. The Milky Way offers no single travel time because the traveler, vehicle, route, and meaning of crossing all matter. Every realistic answer remains immense. Imagine the departure from one outer edge of the galaxy. Behind the vessel lies a sparse region of stars and the darkness beyond the halo. Ahead, the Milky Way fills the sky as a luminous river with no visible end. The central bulge glows tens of thousands of light years away, concealed partly by vast lanes of dust. At first, the ship moves through widely separated systems. Centuries may pass between encounters. The outer disk contains old stars and a lower concentration of heavy elements than regions farther inward. The travelers gradually enter brighter territory where spiral structures carry gas, young stars, and active stellar nurseries. If the vessel moves near light speed, the sky changes through relativistic effects. Starlight ahead shifts toward higher energies and concentrates into a smaller region. Light behind shifts toward longer wavelengths. The galaxy no longer resembles the serene spiral imagined at departure. Motion transforms radiation into a hazard. Thousands of external years pass during the approach to the center. The ship crosses regions whose light once required generations to reach its starting point. It enters the future of systems that appeared ancient when first observed. Maps update continuously as stars reveal their later positions. After the midpoint, the vessel turns and begins slowing. The far half of the galaxy rises ahead. The passengers carry no current knowledge of it. Every observation made before departure showed a place tens of thousands of years younger than the one awaiting them. Arrival occurs beneath unfamiliar stars. The journey has connected two edges of one galaxy while separating the travelers from the age that sent them. A slower ship would experience a different story. Generations would live beneath artificial skies, knowing the galaxy through sensors and inherited maps. Children would learn that the current crew had crossed a fraction of 1% of the route. Adults would die after contributing an almost invisible advance. The central challenge would become psychological scale. Human life gains meaning through goals that can be reached, witnessed, or handed to known descendants. A million-year crossing places arrival beyond every natural chain of personal memory. The mission must create value within the journey itself. Habitats could develop cultures unrelated to the distant destination. New languages would name parts of the ship. Festivals would mark repairs, course changes, and passages near stars. The vessel's history would become deeper than the history of the planet that built it. Some inhabitants would look outward and see the Milky Way as their true environment. The ship would move within a galaxy rather than toward an edge. Crossing might lose importance. Remaining alive, learning, creating, and encountering new systems could become sufficient. The journey could continue after its original meaning faded. Institutions sometimes outlive their purpose because routines, authority, and identity form around them. A society might steer toward the far edge for thousands of generations without remembering why completion mattered. When arrival finally came, its inhabitants might feel little connection with the first departure. They would have crossed the Milky Way because their whole civilization had always been crossing it. The galaxy itself provides a different clock. The Sun takes roughly 250 million years to complete one orbit around the center. Since its formation, it has circled the Milky Way only a few dozen times. Human civilization occupies an almost invisible part of one galactic year. A light-speed crossing of 100,000 years equals less than 1,000th of the Sun's orbit. From the galaxy's perspective, light moves quickly enough to connect the disk before its large-scale rotation changes dramatically. For human beings, the same interval contains thousands of generations. This contrast explains why the Milky Way can behave as one gravitational structure, while remaining inaccessible to living travelers. Gravity, radiation, and stellar motion operate through long timescales. Biological lives occupy far shorter intervals. The galaxy's dimensions match the rhythm of stars rather than the rhythm of minds. A civilization seeking to cross must either increase speed toward the cosmic limit or change its relationship with time. It can extend life, slow consciousness, build generations, replicate machines, or accept that the traveler arriving will differ from the traveler departing. No propulsion system can make the Milky Way small in the galactic frame. Relativity can make it shorter within a fast-moving ship. Civilizational continuity can make long-duration survivable through succession. Every solution transforms the beings undertaking the voyage. The real barrier may lie inside the definition of a traveler. A human body lasts decades. A culture can last centuries. A species may last millions of years. Information can persist longer when copied and repaired. The form capable of crossing determines the answer. The far side of the Milky Way exists today, though humanity cannot see its present condition. Dust blocks many lines of sight, and every observation arrives after tens of thousands of years. Stars there may host planets, oceans, life, and civilizations whose current histories remain hidden. A ship departing now would aim toward a future reconstructed from old light. It might choose a promising world detected through instruments, knowing that the planet would age throughout the voyage. At 10% of light speed, a destination 70,000 light-years away would be reached after 700,000 years. The observed planet could undergo geological or biological transformation long before arrival. An intelligent society detected through artificial signals would pose an even greater uncertainty. Its transmission might already be tens of thousands of years old. Sending a ship toward it adds further delay. The civilization could disappear, migrate, transform into machines, or spread across the region before the travelers arrive. The destination could also detect the approaching vessel. Depending on speed and visibility, warning light from the launch may arrive only slightly before the ship. A near-light-speed craft offers little time for the receiving society to respond. The arrival of a massive relativistic object could be interpreted as a threat. Crossing the galaxy toward inhabited space would require communication, caution, and trust across intervals that destroy ordinary diplomacy. The safest destination may be an empty region. The most meaningful destination may be one capable of answering. A galactic crossing therefore involves uncertainty at both ends. The ship leaves a world it cannot remain connected to and approaches a world it cannot know in its present state. One day, humanity may possess engines capable of reaching a tenth of light speed. Nearby stars would become attainable over decades. Colonies could spread through the local region. Each success would make the Milky Way appear more accessible on maps. The first 100 stars would remain a tiny island. A sphere 100 light-years across covers only a minute fraction of the galactic disk. Expanding to 1,000 light-years still leaves most of the Milky Way untouched. The galaxy's full scale emerges only after local interstellar travel becomes ordinary. A civilization could spend 10,000 years exploring and remain close to its origin by galactic standards. It could fill a region containing millions of stars while occupying a small patch of one spiral structure. Its citizens might consider themselves galactic while the far side remained as distant as ever. This progression resembles walking along a coast whose full length cannot be seen. Every completed stage reveals another scale. Reaching Proxima Centauri proves that interstellar travel is possible. Reaching the galactic center proves that a civilization can endure for immense intervals. Reaching the opposite edge proves that life can propagate across the entire stellar disk. The final achievement may never produce a single famous arrival. Expansion could proceed in countless directions, with different branches reaching different boundaries. Historians may be unable to identify one vessel or one date when the galaxy was first crossed. The Milky Way could become inhabited gradually, until descendants discover that their oldest and most distant branches now occupy opposite edges. The crossing would be recognized after it had already occurred. The answer also depends upon whether humanity seeks to cross empty space or understand what lies along the way. A vessel racing near light speed would pass stars too quickly for detailed exploration. Slowing near each system would consume energy and extend the journey. A true survey of the Milky Way would take far longer than a straight crossing. There may be hundreds of billions of stars. Visiting each one sequentially would be impossible within any useful interval. Exploration must branch. Millions of probes could divide the galaxy into regions, sharing discoveries through delayed networks. Mapping the Milky Way becomes a distributed project. Signals from distant explorers return slowly. By the time a central archive receives a complete survey, many observations have become ancient. Planets change, civilizations develop, and stars move. A perfect current map remains impossible because the speed of light limits how quickly information can be assembled. The galaxy can be crossed faster than it can be fully known. A ship follows one narrow route through an enormous volume. It passes within light years of countless systems without seeing their worlds closely. Completion of the physical distance leaves most of the Milky Way unexplored. This distinction matters because human imagination often treats crossing as possession or understanding. Traveling from one edge to another provides a thread through the galaxy. The surrounding stars remain worlds of their own, separated from the route by distances capable of consuming additional years. The first crossing would reveal the Milky Way's scale while touching almost none of it. Perhaps a beam of light is the only traveler that crosses naturally. A photon emitted near one edge enters interstellar darkness and moves at the universal limit. It needs no fuel, food, repair, or purpose. Along the path, it may pass stars, dust, planets, and empty regions without experiencing an ordinary passage of time in any valid rest frame. From the galaxy's perspective, the crossing consumes 100,000 years. Civilizations can rise during the flight. Species can evolve. The photon continues until matter absorbs it, or cosmic geometry carries it elsewhere. Human beings are made from matter and must carry mass, memory, protection, and life. Every kilogram demands energy. Every living system creates heat and waste. Every mind requires an environment. Our journey time expresses the burden of bringing a world through the galaxy. A radio signal carrying human language could cross at light speed. Its arrival would complete the distance without transporting a person. Perhaps the earliest human crossing of the Milky Way will belong to information. A message, genome, artificial mind, or compressed cultural archive sent toward the far edge. The receiver may open it 100,000 years later. The civilization that transmitted it could be gone. The message would represent a successful crossing and a memorial to the world that began it. Matter travels slowly because it must survive the road. Information can ride upon light, though the sender cannot follow at the same speed. Standing beneath the night sky, the Milky Way seems close enough to be a cloud. Its light stretches from horizon to horizon. The galaxy appears to surround Earth because Earth lies within it. Distance is compressed into brightness, and tens of thousands of light years gather into one pale band. A person can cross that band with a glance. Imagination moves from one side to the other before a heartbeat ends. The physical journey demands a duration longer than nations, languages, and perhaps humanity itself. At light speed, 100,000 years pass. At Voyager's speed, more than 1 billion. At the speeds of plausible future interstellar craft, millions or hundreds of thousands of years remain. Relativity may allow passengers to experience less, provided their ship approaches the limit with unimaginable energy and protection. The galaxy can also be crossed through descendants colonies, self-replicating machines, or messages. Each method carries a different part of humanity. Bodies, genes, cultures, instructions, and memories do not share the same requirements. No answer preserves every familiar feature of travel. A rapid subjective crossing abandons the traveler's original era. A generation ship abandons the original passengers. A replication wave abandons a single continuous vehicle. A light signal abandons physical presence. The Milky Way permits crossing only when the traveler accepts transformation. Far in the future, a vessel may reach the outer darkness beyond the opposite rim. Behind it, the galactic disk will glow across the sky, containing every star passed during the voyage and every history that unfolded beyond communication. The travelers may carry records of Earth, though Earth itself will exist tens of thousands of years beyond the latest message they received. They will measure the remaining density of stars and agree upon a boundary. Engines will slow, instruments will turn back toward the luminous structure. A final entry will be added to an archive whose oldest pages were written beneath another sky. The crossing time will depend upon the method that brought them there. Perhaps millions of years passed through generations. Perhaps a near light-speed crew aged only decades while the galaxy advanced through an age. Perhaps machines copied themselves from system to system until one branch reached the edge. Every route will reveal the same truth. The Milky Way was never a distant object waiting above Earth. It was the environment that contained every stage of the journey. The travelers crossed their own cosmic home. The achievement will appear immense within the history of intelligence and almost invisible within the history of the galaxy. Stars will continue orbiting. Clouds will collapse. The central black hole will remain in darkness. No physical boundary will mark the completion. A message may be sent toward the starting edge. It will need another 100,000 years to cross the spiral. The travelers will know that no immediate answer can come. Their voyage will be complete. The story of that completion will still have the entire Milky Way left to travel.